Now that we've talked about setting up our hypotheses for a hypothesis test related to proportions, calculating a test statistic, and checking the assumptions to decide whether we can even do a problem like this, we can now talk about actually finding p-values and then do an example where we go through an entire problem from beginning to end. All right, so just like in previous problems, you'll notice that's kind of a theme, I keep saying that, we're going to find our p-values sort of similarly to how we did in the one sample, paired samples, and two independent samples problems. We're going to look at our alternative hypotheses. We're going to find the sign that we have in there. And if we've got a less than sign, we'll think of it as sort of like an arrow pointing to the left, telling us that we should find our test statistic. In this case, I'm going to use -1 for these pictures, and then shade everything to the left of that. If we have a greater than sign in our alternative hypothesis, I'll still find my test statistic on the bottom, but I'll shade everything to the right of it. And if I've got a not equal to sign, I'm going to find my test statistic, but I'm going to put both a negative and a positive version of it on the bottom, and I'm going to shade everything outside of both of those. And so you'll notice that in StatKey, I would do that by choosing left tail for this one, right tail for this one, and two tail for this one. And in each case, the p-value would be, it looks like 0.159 here, 0.841, and then for this one, I would have to add these two values, so 0.159 plus 0.159 to get my p-value. So let's talk about what an entire problem would look like. And we're going to go back to the cane toad example. So this says 18 green beads out of 30. That means 18 female cane toads. This is adapted from an example that we would have done in person if we were on campus. All right, so let's say that I had 18 female cane toads out of my 30. Well, if I'm going to work through a problem, let's say that my hypotheses are p equals 0.4. So this means that I think that 40% of the cane toad population is female, versus an alternative that just says p is not 0.4. So something other than 40% of the population is female. So the steps that I'm going to go through, first I need to figure out what p hat is. What is my sample proportion? Well, 18 out of my 30 cane toads were female, so I'll take the number of female cane toads divided by 30, and I get a sample proportion of 0.6. So in my sample, 60% were female. I think that maybe 40% of the population is female, and so there's two possible ways that I would have arrived at a sample proportion like this. One way is that the null hypothesis is true, and just due to random chance, I got something that was a bit higher than that. The other way is that the alternative is true, and maybe this actually represents something more like what the population proportion is. So I need to go through the steps of a hypothesis test to decide which of these explanations makes sense. All right. So one way I can do that is I can calculate my test statistic. And so I'm going to be comparing my data to what my null model said. So in this case, I'll take my sample proportion 0.6. I'll subtract off p from my null model, which was 0.4. Underneath the division sign, I'll take the square root of p times 1 minus p over n. And so you can see all of the numbers that are going into this here. And when everything's said and done, I get a test statistic of 2.236. So if I looked at this picture up here, that would be maybe right here on my picture. And so you can start to see that, okay, well, if my alternative says not equal to 0.4, I would shade, say, this little area up here, and then I would shade this area down here. And at this point, I'm not really sure if that's bigger or smaller than 0.05, so I would need to actually use StatKey to find it. And you can see, here is what that looks like when I do it. So I choose normal when I go to StatKey. It pops up this picture. I click two tail because my alternative hypothesis has a not equal to sign. I put my 2.236 down here. I put a negative version of that over here, and this side has an area of 0.013. This side also has an area of 0.013, which tells me that my p-value is those two things added together. So I'm going to get a p-value of 0.026. And what we said when we started this was that there were sort of two ways that we could get a number like this. What my p-value is telling me is that if this null hypothesis is really true, there's a pretty small chance that I would see a sample proportion like the one that I saw. So it's possible that this is true and something like this happens, but it seems pretty unusual that this would happen in that case. So the way that we've decided we're going to handle this is we're going to sort of flip that around and say, okay, well, if this is really unusual when the null hypothesis is true, then I think that this is actually sufficient evidence that the alternative is true. So in this case, if I got 60% of my sample was female cane toads, that would be sufficient evidence that the population proportion of cane toads that are female is not 0.4. So again, I don't know exactly what it is yet. I could do a confidence interval to get a better guess at that, but I seem like I have sufficient evidence that it's not 40%. And that was actually our guess for what we thought it was when we looked at that picture at the beginning. So this is if you had gotten 18 female cane toads out of 30. What I want each of you to do is do this same process for your sample. All right, so if you haven't done that yet, you might want to pause this video and do that right now. If you actually had 18 out of 30, try using 9 just as another example. And I'm going to go through it for my sample right now, which was 13 out of 30. But like I said, do this for your own sample first, pause it, then come back, and you can look at what I did for my sample as well. So here's what I've got for my sample. I had a sample proportion of 0.433. All right, so same hypotheses. The null says the population proportion is 0.4. The alternative says the population proportion is not 0.4. I'll put my sample proportion into my test statistic formula. So 0.433 minus 0.4. I'm dividing by this stuff on the bottom here. And I end up getting a test statistic of 0.369. So you might already have a sense that that seems pretty close to the center of my picture. And if I go to StatKey, again, I'm going to choose two-tail. I'm going to put 0.369 here, but then I need to also put the negative version here. And what you'll see is that a lot of this picture is shaded. So what this is telling me with my p-value of 0.712 is that if this really is the population proportion, it's not at all strange that I would get a result like this, because things like this happen quite a bit. About 70% of the time I would get results sort of like this. So in this case, even though I didn't get exactly 0.4 for my sample proportion, this does not seem like sufficient evidence that the population proportion is anything other than 0.4. Now again, remember, this doesn't mean I think the population proportion really is 0.4. It just means I think that it could be. All right? And I mentioned that I would tell you the true answer at some point later in the notes. So the actual population proportion was really 0.375. So it was close to 0.4, but it wasn't exactly that. And so I'm not saying, again, that I think it is 0.4. I'm just saying my results would make sense with that theory. I'm going to calculate a confidence interval coming up, and you'll see that my results would actually make sense with lots of theories. There's lots of different null hypotheses that would lead me to sample proportions like this. All right? So if you had gotten this result, that would seem like good evidence that the population proportion was not 0.4. Most likely, most people didn't get this result because the population proportion was only 0.375. Probably a lot of you will end up in cases like this, where even though this isn't true, you're really not able to rule it out because it's pretty close to true. So we'll stop here and pick up for the next part of the notes with talking about confidence intervals a little bit more.